All right, hello everybody. Welcome back to Physics 425. When we last left off, we were talking about Joule-Thomson expansion, and so here I have a little bit of a review of some of the things we were talking about. First, the apparatus consists of a long insulating tube, and in the middle of that tube there is a porous plug. The porous plug allows gas to pass through, but slowly. The reason that it's needed is because in the Joule-Thomson expansion, we require a pressure difference between the two sides, between the left side and the right side. So if the plug let gas flow through very easily, then you wouldn't be able to establish a pressure difference between the two sides. The idea is that we're going to use the two pistons. They're going to move simultaneously. The piston on the left, side 1, is going to be pushing gas through the plug, and the piston on the right, side 2, is going to be moving to the right to allow the gas to enter. The pistons are moved in such a way that the pressure P1 on the left-hand side stays constant, and the pressure P2 also stays constant on the right-hand side. We did some analysis of the so-called Joule-Thomson coefficient, mu, and the result that we ended up with at the end of the last video is right here. And the important point was that if the Joule-Thomson coefficient is positive, then the temperature of the gas T2 on the right is less than the temperature of the gas on the left, T1, and we get cooling. On the other hand, if the Joule-Thomson coefficient is negative, then the gas heats as a result of this expansion. And so what we need to do now is, if we wanted to, for example, evaluate the partial derivative in the numerator of the Joule-Thomson coefficient, we need to have a model for how our gas behaves. So to go further, we need to model how real gases behave, i.e., we need an equation of state. Actually, before we think about our interacting gas, let's just try the ideal gas, which is a system of non-interacting particles. Okay, so we know the equation of state is PV equals NKBT. And so if we wanted to evaluate this derivative, the partial derivative of volume with respect to temperature, let's see, we divide by P, then we take the temperature derivative, and we would get NKB over P. But of course, going back to the equation of state, NKB over P is just equivalent to volume over temperature. And so then when we consider the numerator of the Joule-Thomson coefficient, it's T times this partial derivative minus V. And so that means T times the partial derivative minus V is going to be equal to T. The partial derivative we said was equivalent to V over T, and then we minus V, and that becomes 0. And so in this case, the Joule-Thomson coefficient is neither positive or negative, and what that tells us is that there just is no temperature change when we think of an ideal gas, and so T1 is equal to T2. So for an ideal, non-interacting gas, we find that the Joule-Thomson coefficient is equal to 0, and therefore T1 is equal to T2. So there's no heating or there's no cooling. So we'd like to do a similar sort of thing for an interacting gas. Before we can do that, we need to develop the equation of state for an interacting gas. And the model that we're going to work with is the van der Waals gas. So the model has a couple of assumptions. In an ideal gas, you assume that the particles are point-like, so they don't occupy any volume. So we're not going to make that assumption, so don't assume the gas particles are point particles. We're going to assume that they are hard spheres. Okay, so therefore, when they're added to some container with some volume V, they occupy some of that volume. So when they're added to a closed volume, these gas particles occupy some space. And so that means the free space goes from V to V minus N times B prime. N is going to be the number of particles, and B prime represents the volume of space occupied by a single particle. So B prime is the excluded volume. I did it again. Excluded volume due to finite size of a gas particle. Right, essentially, B prime is the volume of our hard sphere. Okay, so that's one assumption. So there's going to be a modification to the volume in our equation of state. Another assumption is that we assume that there is a short range attraction between particles. Remember last time we wrote down kind of a potential energy diagram for a pair of interacting particles, and it looks something like this, where there was some equilibrium distance. X is the distance between particles, and we said this was the repulsive regime, where two particles get so close to each other that they repel each other, and this was the attractive regime. So we're going to assume that we're to the right of this x0, and so we're somewhere over here where the density of particles has an average separation of x between particles that's greater than x0, and so there's some attraction between particles. Okay, so let's kind of sketch a little container of gas particles, and first we'll think about some of the particles that occupy a volume that's somewhere in the middle of the container. So particles in the center don't feel a net force to the left or right or up or down or into the screen or out of the screen. That's because if I take a particle right in the middle here, it's surrounded by an equal number of particles immediately to its left and it's immediately to its right, and it's attracted to all of those particles equally, and so the net force is, there's no net force in a preferred direction. Okay, and then what we could do is we could think about some particles over here near the wall of the container. So particles near the container wall, they do feel a net force. And why is that? It's because if I take a particle over here, it's attracted to the particles that are to its left, but because of the wall, there are no particles to the right, and so it's not attracted to the non-existent particles on the right-hand side. And so there's a net pull for that particle near the container wall inwards. And so in the way I've drawn it, a net pull to the left. So they feel a net inward force because of the absence of particles near the container wall. Okay, so let's see, the net inward force on surface particles is proportional to the density of particles, right? So if I'm a particle sitting at the surface, if the density of the gas is high, then there's going to be more particles pulling me inwards, and so the force that I feel increases. As you increase the density, there's also more particles that are right at the surface, and so the number of surface particles increases. That means they're being pulled in more, and there's more particles being pulled in, and the result is that the pressure on the vessel goes down. So the number of surface particles is also proportional to the density. And so the inward force and the number of surface particles both go as n over v, and so therefore what we expect is the pressure on the vessel walls in an ideal gas, if it was P, it's going to be reduced by an amount. A prime is some coefficient, but then there's two factors of n over v due to the 2 points that we've made up here. Okay, so these are the two ideas that are going to go into our van der Waals equation of state. If we were to start with the ideal gas equation of state, PV is n kBT, let me divide by the V. So this is for an ideal gas. Our modifications are going to take this equation of state to the following. Let's do it this way. Let's do P is going to be n kBT. We said the volume was going to be reduced because we're thinking of hard sphere particles, and there's our volume reduction. And we've calculated pressure, but we said the pressure was going to be reduced by this amount, and this is going to be our van der Waals equation of state. We're going to make a few manipulations to this equation of state, and then we'll go back to our Joule-Thomson coefficient and try to evaluate the numerator in that coefficient and see what happens. Okay, so let's divide by kBt, and then what we're going to get is n over, in the denominator, I'm going to factor out the v, so we get 1 minus n b prime over v is equal to, minus a prime, we had to divide by kBt, and then we have n over v squared. Okay, so this is n over v, 1 minus nb prime v to the minus 1 minus a prime kBt n over v squared. So it would be reasonable to assume that the excluded volume, nb prime, due to the presence of the particles, is much less than the volume of the container. So if the excluded volume is much less than the volume of the empty container, then we could make the approximation. This is the binomial approximation, that 1 minus a small number to a power is approximately equal to 1 minus the power times the small number, which ends up being, in our case, 1 plus n over v b prime. Okay, so we'll make that change. And when we do that, P over kBt is going to be approximately n over v, and then our approximation was 1 plus n over v b prime, and then we still have minus a prime over kBt n over v squared. Or let's multiply both the left and right hand side by v over n. So then we have PV over n kBt. If this was an ideal gas, that would be equal to 1. Okay, so now we multiply the right hand side by v over n, and we'll get 1 plus n over v b prime minus a prime kBt n over v, which is equal to 1 plus n over v b prime minus a prime over kBt. Right, and so there's our factor of 1, and then this other term, the plus whatever, is like a van der Waals correction for an interacting gas. Okay, so we're going to make another approximation to make our calculation easier. In an upcoming assignment, you're going to repeat the type of calculation we're doing now, but some of the simplifying assumptions that we're making you're not going to use in your assignment, and you'll get a better result than we're about to calculate. Okay, so on the right-hand side, what we're going to do is we're going to make the approximation that the n over v factor multiplying the b prime minus a prime term, we're going to assume that we can use the ideal gas approximation for that factor. Okay, again, you'll do better in an upcoming assignment. And so if we do that, then we get PV over NKBT is 1 plus N over V, we're going to approximate as P over KBT. And then we have our B prime minus A prime over KBT. Or what we want to do in our Joule-Thomson coefficient is to take a derivative of the volume. So let's calculate the volume. So now we multiply by N KBT over P, and it has to multiply all this stuff. 1 plus, I'll put the 1 over KBT here, and then I'll have a B prime minus A prime over KBT, and then we have our factor of pressure. Okay, good. So I think now we're ready to evaluate the partial derivative of V with respect to T at constant pressure. And so let me just scroll back here. And why are we evaluating this? It's because we want to calculate the Joule-Thomson coefficient, and there's the partial derivative in the numerator. Okay, so we're going to have to do a few chain rules here. So we'll have to do this carefully. First, the coefficient out front here has a temperature, so we'll first deal with that derivative. We'll get NKB over P, and then we have to multiply by all of the stuff that was in the brackets. Okay, and then we add to that the original coefficient, NKBT, and then we have to take the temperature derivative of what was inside the brackets. But again, we have to be careful because there's another chain rule because we have temperature in two places. So let's first deal with the 1 over KBT coefficient inside the brackets. So we're going to get a minus 1 over KB, and then we'll get a T squared, and then it multiplies the B prime minus A prime over KBT and P. And then we have to write down the, let's see, we'll get plus 1 over KBT, and then we take the derivative over here, and we have a minus A prime over KB, and then we'll get a minus 1 over T squared, so overall it's plus A prime over KB T squared, and we still have pressure. Okay, so I think that's the derivative. So NKB over P, and so what is all the stuff we have? We have a 1 plus 1 over KBT B prime minus A prime over KBT P. So that's, I haven't changed anything there. What I'll do is I'll take this temperature factor that's out front and distribute that temperature. So we'll get a minus 1 over KB, the T squared becomes T, then we get B prime minus A prime over KBT P, and then we'll get, let's see, the T's are going to cancel here, so we'll get a plus A prime times P over KBT squared, and then close bracket. what's nice about this result is that these two large terms inside cancel exactly, and we're left with that the volume derivative with respect to temperature is equal to nkb over P, and we just have a 1 plus A prime times pressure over kBT squared. Okay, good. So recall that our full Joule-Thomson coefficient was given by T times this derivative minus volume over the heat capacity. So if we do that, what we find, let's do just the denominator of this coefficient. So we're going to multiply it by T, and so what we'll have is an nkBT over P 1 plus A prime P over kBT squared minus the volume. Now we have to be a little bit careful here, because in our van der Waals expression, this is what we calculated for the volume. So we're going to write down all of this when we subtract the volume. So we have minus nkBT over P, and all of that stuff was a 1 plus 1 over kBT B prime minus A prime over kBT and pressure. Okay, the factors are the 1 terms cancel because we're taking the difference. And so what we're left with then is nkBT over P, and then we have a prime P over kBT squared. In the second term, we have an A prime, we have kBT squared and P, and we have 2 minus signs. And so these two terms are the same, so we end up with a 2 A prime P over kBT squared, and then we have a minus B prime P over kBT. Okay, so we can cancel a kBT, and we could cancel a P, and so what we're left with is N 2A prime over kBT minus B prime, or dividing this by now the heat capacity gives us the Joule-Thomson coefficient. N over 2A prime kBT minus B prime over the heat capacity at constant pressure. What we said in the beginning was that if the Joule-Thomson coefficient is positive, we'll get cooling. If it's negative, we'll get heating. And we can see now where the difference in signs comes from. It comes from the relative size of the A prime and B prime coefficients. If A prime is really large, then we'll get a positive Joule-Thomson coefficient. depending, I guess, on the temperature. And then if B prime dominates, then we'll get a negative Joule-Thomson coefficient, and we'll get heating. So one way to think about this is that at low temperature, the 2A prime over KBT term dominates. In this case, mu JT is going to be approximately 2NA prime over CP KBT, and which is positive, and we get cooling. At a high temperature, because we're dividing by a large T, the B prime term dominates. And we get our Joule-Thomson coefficient is approximately minus NB prime over CP, which is, of course, negative, and we get heating. There's a special temperature where the two terms will just cancel each other out. That's called the inversion temperature. So at the inversion temperature, let's say T inversion, the Joule-Thomson coefficient is 0. This occurs when, let's see, 2A prime over KBT inversion minus B prime is equal to 0, and therefore T inversion is equal to what? It's 2A prime over KB B prime. Okay, so in our picture then, what we've got is below T inversion, oops, we get cooling because mu JT is positive, and above T inversion we get heating because mu JT is negative. We could kind of draw a diagram of this situation. So here's pressure and temperature, and so if we indicate our inversion temperature somewhere on this graph, then at high temperatures we get negative coefficients and heating, and at low temperatures we get positive coefficients and cooling. So in practice, if you were to actually do an experiment and measure the Joule-Thomson coefficient, you would find that it also depends on pressure. Depends also on pressure. See, our calculation for the Joule-Thomson coefficient has a temperature dependence, but no pressure dependence. And so, you know, I've made this plot as if it's a function of pressure, but nothing's changing as we vary the pressure here. So in assignment number 2, you will calculate this coefficient for the same van der Waals equation that we developed, but you'll do it more carefully. So specifically, what you're going to do is, in your calculation, you're not going to make the following approximations. One of the approximations we made was that this 1 minus n over v times b prime inverse of that was approximately by the binomial approximation 1 plus n over v b prime. So you're not going to do that. And at one step in the calculation, we had this n over v factor, which we just replaced with kBt, p over kBt, based on the equation of state for an ideal gas. And so we made this approximation on the right-hand side of one of our expressions. Okay, so you're not going to do that. Your calculation is going to be a little bit more difficult, but what you should find is that if you make this diagram of temperature versus pressure, and you try to show how the Joule-Thomson coefficient is behaving, you'll find this like little bubble. And inside this bubble, you'll find that the Joule-Thomson coefficient is positive. And so it's positive in here, and you're going to get cooling inside this bubble. But everywhere outside the bubble, you'll find a negative coefficient, and correspondingly, the gas will heat. This curve here, this boundary, is where the Joule-Thomson coefficient is equal to 0 on the boundary. So for us, our boundary was a straight line, right? The boundary was this dashed line here. You're going to find a more intricate boundary condition, and this is called the inversion curve. So essentially what it's telling you is that the inversion temperature, right, so T inversion 1 is dependent on the pressure. So at P1, there's a T inversion 1, and in fact, there's a second inversion temperature. I better not call that 2. So this is another inversion temperature when the pressure is equal to P1, so I'll call it T inversion 1 prime. And so what that means is that if you start with your gas too warm on the left-hand side of your Joule-Thomson apparatus, when you do the expansion, it'll heat. If you lower the temperature, there'll be a big region of cooling, but if you start with your temperature too low, you'll go back to heating. And so there's an optimal region where you have to get to in order to have your Joule-Thomson expansion result in a cooling of the gas. If you're working with helium, it turns out that you can cool helium gas enough using a Joule-Thomson expansion that it will start to liquefy. And so the final comment I'll make is that you can liquefy the helium-4 isotope of helium, that's the dominant, our most abundant isotope, can liquefy helium for using a Joule-Thomson expansion. Okay, so using the methods that we've imagined so far, we could use a two-stage Stirling cryocooler to take our helium gas from room temperature and cool it maybe into the range of around, I don't know, between 10 and 20 Kelvin. And then you could take that pre-cooled gas and you could do a Joule-Thomson expansion, and it will cool enough that the gas will start to liquefy. And so now you can make a bath of liquid helium-4. So at 1 atmosphere of pressure, the boiling temperature of liquid helium-4 is about 4.2 Kelvin. So now we're just 4 degrees Kelvin above absolute zero, and we have this bath of liquid helium. What we're going to do next is we're going to go from, if you have liquid helium boiling at 4.2 Kelvin, how could you take the temperature of that helium bath down further? And that's what we'll start with next time. All right. Thanks for